when you're actually talking to people, if you have questions directly, it's the best way. Now, what I do also, I might as well tell you this, is at the beginning of every class, I say, are there any questions? Oftentimes, there's certain homework problems that are confusing. And I will spend time at the beginning answering those questions for everybody, once and for all, hopefully, and then moving through to the theory. And I don't like to make this dry. The way I approach this, I'll present theory, then apply it to a problem immediately. I try to make sure if there's any theory, it's applied and people understand it, okay? Now, we're going to talk about this. We start with probability. Before I even get to Venn diagrams, everybody has an idea about that. Probably the most common thing that people talk about is dice. And with dice, if you're talking about a single die, you have basically a possibility of a 1, a 2, a 3, a 4, a 5, or a 6. Those are the only possible things. They're called outcomes. Does everybody follow me on this? You don't have to take careful notes on this, but just listen. It makes perfect sense. So if we were to actually try to create some way of mentally understanding this, we talk about something called the set of all possible values. This is that box syndrome. You'll see this type of thing, and a lot of times the discussion gets very deep mathematically. Don't worry about it. The set just represents these outcomes. If you had a deck of cards and you talked about the possible values of the cards, there's 52, right? Throw the jokers out. All right, you get the idea. Follow me on this? Now, if you have that and you look at this, and I'm going to say that A just represents 1, 2, or 3, all right? So here, I'm just going to show you something, A. It just represents those numbers. Does everybody follow me? So what is the probability, and the symbol is P, the probability of A if you throw the die one time? You got me on this? What is the probability of one of those numbers coming up? Now, your common sense is right on this one. I'm telling you this. Well, you would say, well, what is the probability of a 1? I know you know it. It's what? 1 over 6. 6 possible outcomes. If a 1 comes up, it would be 1 out of 6 is the chance of that. That's called a relative frequency. Does this make sense to you? There's nothing deep here. It's as obvious as the nose in your face. All right? What's the probability of a 2?
Also 1 over 6.
Probability of a 3.
1 over 6.
Okay? Now I'm going to show you. This is one way to do it. They're all mutually exclusive, meaning if a 1 comes up, a 2 can't. If a 2 comes up, a 1 can't. That's the only thing mutually exclusive means. If it's either or, it can't be both. Y'all with me on this class? So if I take a look at the probability of A, it's really going to be just the probability of a 1 plus the probability of a 2 plus the probability of a 3. It's because they're mutually exclusive. Do y'all follow me? Now, another way to think about this is probability of A. Well, these are 3 values out of possibly 6 values, right? What is this going to be equal to, by the way? That's 1, 6, 1, 6, 1, 6 is 3, 6, or 1/2. Can y'all follow me? Nothing deep. Matter of fact, this is so simple, it's almost, why am I here? I mean, you know this from the time you're probably 5 years old. You can see that, right? All right, you can look at it the way I did it, where because they're mutually exclusive, and by the way, I'm not going to break this down, but like the 1 would be here, there would be a 2 here, and maybe 3 would be everything else. Do you all follow me? That would represent the area in some way, shape, or form would be proportional to the outcomes, the likelihood of the outcome. Another way to do it is what? I got 3 values of a possible 6, just take a 3 by 6, right? If the likelihood of each one of those events is the same. Do y'all follow me on this? Now, in the future, you're going to see, we're not going to take a normal die. We're going to say, well, the likelihood of a 1 might be 0.025, of a 2 might be 1 over 100, of a 3. Y'all follow me on this? Then, the probability of The fact is, if this is all possible outcomes, the probability of any one of these outcomes happening, the probability of all of these outcomes, the probability of a 1, 2, 3, 4, 5, 6, the probability of any of those has to be 100% or 1. Y'all with me? You have to have a guarantee that if the die is rolled, something happens from 1 to 6. That's what I mean by what I'm trying to get. Y'all with me? It's fairly straightforward. All right, now we've got that, and I try to give you a representation of this. I'm going to continue on with this Venn diagram stuff. So when we talk about a Venn diagram, we talk about S representing, it's usually a rectangle, all possible outcomes. Then we talk about, regardless if it's die rolling, it doesn't matter what it is, anything with a possible outcome, all right? If we have A here and B here, there's no overlapping area. These are called mutually exclusive, and it should make perfect sense to you. Do y'all follow me on this? If you see this, and I have several points to cover, but I'm trying to do this in a way that makes logical sense to you. If I had something like this, if this is all possible outcomes, and this is A, and this is B, now you see there's overlapping area. Are you with me? Now I'm going to bring in some symbolism that I think you might have had in your digital courses, but I'm not certain. That's the problem. It's been so long ago. I took my stuff. My gosh. Over 40 years ago, courses, digital and stuff like that. It's things have changed. You know, did you guys build JK flip-flops and all that? Yeah. Okay, well that hasn't changed, at least they're somewhat relevant. When you take a look at this, all right, I'm going to talk about some things, some symbolism. When we talk about this operator, A union B, are you familiar with that symbol? Where did you get that, digital? Or where?
Some math somewhere.
Mathematics?
Discrete structures. But I think only computer engineers take that. I don't think only takes that.
Never taken this.
I don't know what course. We used to get that in digital. We would use these symbols. All right, what it means is anything that is either A or B. So if I was to show you the area, it would be all of that. It would be all of this. Do you all follow me on this, class? Over here for this one, it would be everything in there. I'm just trying to give you a visual on this. Now, if you take a look at and there would be a probability of A or A and or B. You all with me on this, class? But for now, we're just doing symbols. If I say A intersect B, I don't really care what that symbol's called. That used to be an AND gate symbol, believe it or not. You know an AND gate? It would be, what is an AND gate's output? If it's 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, right? That was a symbol that they, at least at one time, used for it. Did they ever use that kind of stuff? They did? Oh, fantastic. I'm still relevant a little. But if you look here, what is this? Well, this is the null set here. That's 0. Is there any overlap at all? You see how there's nothing? Y'all with me on class? That's all it means. So what's the probability of A and B simultaneously occurring? 0. Y'all see this? This is exclusive. This would be like the numbers 1, 2, 3, 4, 5, 6 in die roll. You can't have both of these events occurring at the same time. Mutually exclusive. That would be 0. Over here, what is it? If I take a look at A and I have intersect B, now I'm just going to show you it would be this area there. Can you all see it? That's the intersection. Now when you talk about probability and you talk about, and again this is, I'm on purpose being obscure about what events I'm talking about. This pertains to all events. And you notice these are only 2D drawings. there are probably ways of rendering this in 3D, but it would be insane for me to try to show you some of this stuff if you get these complicated sets. Everything stays 2D only, planar, for everything we're going to be doing. So if you look at this, if we talked about the probability of A intersect B here, it would be 0 as well. And that should make perfect sense. Is that, you with me? Come over here, and talk about the probability of A intersect B from the drawing above, right here. Well, if you look at this, and this is the one I want to write down and make sure you see what I'm about to say. This is the first thing that becomes a little more important, so you're going to have to be attentive to. Y'all with me on this? All right, well, I can say it is the probability of A plus the probability of B. Now, look, when I get that, think of these as areas. Probability of A would be like the area of A over S. Do y'all follow me on this? If S was proportional to all possible likelihoods, then the probability of A divided by S would be, the actual, you might say the area of A over the area of S. It's really the probability of A over S. Well, the probability of S is going to be 1, something. So this is probability of A plus probability of B, but then the problem is I've accounted for this area here twice. Do you all see that? If you take area A plus area B, or probability A, probability of B, you've got to get rid of that area. Do you all follow me? So what you do is subtract off probability of A, and you got to, I used intersect. My bad. I meant to say union. A union B. My bad. I'll make mistakes through this class, but I'll try to correct them as soon as I see. Or somebody else yell at me if it doesn't make sense. Y'all with me on this? I'm trying to find the probability of A and or B. Both of them. Either one occur. So it's probability of A plus probability of B minus the probability of A intersect B. Now, I'm going to give you a specific example numerically in a second, but y'all follow me on this, class? Then we'll do this numeric example, and then I'm going to show you how, let me use this, how this theory will apply to the dye problem. Hopefully, I'll make it simple. With this class, I'll tell you one thing I don't like. People teach it, and they don't have concrete examples after abstract theory. This is real simple stuff, but when it gets complicated, you can really get lost. So every time I put up some theory, if you don't see me go into an example right away, yell at me. Make me aware. Okay, getting back to this thing. So now we're back to the dice. All possible outcomes with a set would be 1, 2, 3, 4, 5, 6. By the way, I'm very casual with the way I define these things. I don't do them exactly with mathematical notation for a reason. We're engineers. We get paid to make things work, not prove theories in journals. Anyway, so this is all possible outcomes. I'm going to call A as the values 1, 3, and 6. I'm going to call B the values of 1, 4, and 5. Are you with me on this? I left out 1. I'm sorry. 2 is not there, but there are 6 values. In other words, there are 6 values, but really there's 1 is redundant in both. You all follow me? All right, so now we draw this. It doesn't matter how you draw it, but I'm going to call this A and this B. And the set, of course, is all possible. With me? Now, what I want to know is, first, the probability of A occurring. I'm not gonna spend time on this one, I think you all can, just probability A. Take one look at that, what is it?
3/6.
I have what? 3 possibilities out of 6 possibilities, right? It's 1/2. How many see this? I could put 1/6 plus 1/6 plus 1/6, but does everybody see this? All right, making sure everybody sees it. It's gotta be 1/2, right? What's the probability of B? Well, 1/6, 1/6, 1/6, you agree? Or 1/2, correct? All right, now what is the probability of A union B? In other words, A and or B, either one, what would it be? Now think back to the second drawing over there. Just think for a second before I go through. How many see it? I'm not gonna ask you to tell me. All right, you see it or not? Well, we got P of A, don't we? And we got P of B, right? What don't we have?
P intersection.
Well, we don't have, exactly, we don't have this. So what is P of A intersect B? Now take a look at that. What's the only intersection point? Y'all see that? What is the probability of that?
6.
1/6, right? How many see this? Can you follow me on this one? I'm really trying to make this as simple and as clear as you can see. So this is 1/6, right? Let's see if this works. So when we talk about this, maybe I better put it down here, probability of A union B, we're going to have just, bless you.
Thank you.
Probability of A, you follow me over there? Probability of A, which is 1/2, plus the probability of B, which is 1/2, or 3/6. Y'all with me on this? Which is 1, but it's going to be minus 1/6, or 5/6. Does that make sense to you? How many see this? Now, when we talk about probability, you'll notice I don't have the percentage. I'm not using a percentage. But what we would say typically, if it's in a percentage, we multiply that by 100. All right, because 100% means everything. That's like the set has a probability of occurring. It's actually called the frequency. But the frequency of events is 1. It's got to happen. And when they talk in percentage, it'd be 100% chance. That's the only difference is the percentage you always multiply by 100 and put that little percent sign. But the implications are the same on both. 5/6 doesn't make sense based on this. If you think about this, this is what we're looking for as a possible outcome. The only outcome that's missing is 2, right? All possible outcomes of 6, these are 5, 5, 6. It should make sense to you. Y'all with me? And it's really, in a nutshell, what I just covered is probably about 10 pages now. Maybe not 10 pages, but more than a few pages in the book. And I'm trying to just make it simple. Very simple and direct. Now, looking at one other thing I want to just cover briefly. I actually want to do a problem in here too. I want to do conditional probabilities before I do a problem. Is everybody kind of understanding what I'm doing here with these Venn diagrams? Venn diagrams are just, they're showing a representation in terms of a very simple plot, or not even a plot, a drawing of how people visualize these kind of events, event spaces. And they try to make it easy. A lot of stuff I do with radar, and that's the primary I'm involved in right now, is work with radar and using neural nets to classify targets. And even in the future, building adaptive radar where it can reconfigure based on the type of terrain and targets we're interested in. Now, the next thing we're going to talk about is something called conditional probability, but it's just a simple extension of reason based on this kind of stuff. So if we talk about conditional probability, And here's my S that represents all possible outcomes. Now I'm gonna go back to this. This is A, and this is B. And I have some sciatica here, and I'm gonna have to have some, I don't know what's gonna happen next, but I'm gonna have a doctor deal with it. And this would be simply, this is gonna be A intersect B right there. Now, if I take a look at that, we've already talked about the probability of A union B, right? Now we're gonna talk about something we haven't. And it means, the way it's represented is this way. If I say I want the probability of A, and then this does not mean division, but if you see this slash B, it means the probability of A given B occurred. Have you seen this notation anywhere? All right, now I know you think divided by. That's logical, that's the symbol. It means if B is given to occur, what is the probability of A occurring? Y'all with me? Now, if you don't have any overlap, if B occurs and there's no overlap with A, well, the probability of A is 0. Do you all see that, class? It's like if A represents heads and B represents tails, if a head occurred, a tail can't. It's that simple. Not in one flip, at least, all right? So when I take a look at this, here's area-wise what happens. I say, well, this is, when I think about it, now I'm going to say B has occurred. So if B occurs, I hope I say this in a way that's meaningful. It means, think of it in terms of area. That red thing has occurred, right? The red just represents the probability of that happening, and it's guaranteed it happened. Well, if that happened, what is the probability of this happening? You all follow me? If this happens, what is the probability of this slice happening? And I'm going to write it down, and we'll talk about it. Well, that would be, it would be equal to the probability of A intersect B over the probability of B. Remember, B occurred. So say, and we'll talk about this. Are you with me on this, class? I'm going to give you an example. Can you all follow me on this? By the way, if this goes to 11, right?
Yes.
All right. If 5 start to get close to running over, yell at me. I have a way of becoming oblivious to time if I'm on point. All right, now look at this for a second. Just think about it. S represents everything, but we don't care about everything. We're saying B has happened. Guaranteed this occurred. We don't know what happened in B, but B has happened. It could represent 1 value, 10 values, 1,000,000 values, but it has happened. So out of those values, then we see this subset here, and we want the probability of that subset or A occurring, right? So it's really a ratio of areas. Can you all see this, or at least appreciate what I'm trying to show you? Even though it's not truly a ratio of areas, you can think of it that way in a very real way if we know the probabilities. So let's go back to throwing a die thing, and I guess I'll do it here. I'll try to do that. Do you need a stand for that?
I'll get something.
Well, you've been holding it. I hate to have you hold it.
It's fine.
Unfortunately. The usual garbage upstairs. Oh, there. I shouldn't say garbage. This is what I was looking for. Staplers are great backstops. See if that works. Anyway, back to this right here. I'm going to try to give you, and I'm trying to do this as simple as possible because at least at this level, you can make the logical extension. The thing, without much trouble. You know, when I was in high school, I don't ever recall having anything with probability. I don't even think a course is offered, but in college, you get this in so many different, I mean, you can take statistics, you can take this course, random signals and systems, you can probably take courses in, like in the philosophy department, in applied logic and stuff that'll have this, but it comes in different forms and it's all the same thing, really. Okay, so let's go and talk about, I'm gonna say A, we'll go back to the die. Event A is 1, 3, 4. And event B is equal to 2, 4, 6. All right? And I'll try to make a drawing that's representative. This is S, so here's my A, not drawing a scale by any means, and here's my B. And now, we're gonna, can you all read that okay, by the way? I'm really not trying to bore you, but I'm really trying to make this crystal clear right here at this part, because the extensions get a little tough. If I take a look at this, and I would ask on a quiz, and this actually is something I would ask, and I say, I want the probability of A, just the probability of A. What would it be?
1/2.
It's gonna be 1/2, it's gotta be. We thought we could go through the 1, 6, 1, 6, 1, 6 thing, but we've done that, right? So it's 1/2. The probability of B? 1/2 too, right? Both of them. Very obvious. And by the way, when you're doing problems on the quiz, don't fly through it, because sometimes you misread something. And I'm telling you, I have seen people make really dumb mistakes because they flew through it in a hurry, because they're bored by it. It's too obvious. Just take your time. All right, now, what is the probability of A given B occurred? Now, here's an application. All right, did I erase that? No, it's there. So, first thing we need is, what is the probability of A intersect B? Remember, it has to be a member of both sets. Well, look up there. What is a member of both sets?
4.
Can you all see that? 4, right? What's the probability of 4?
1/6.
1/6. Now, what is the probability of B occurring? Well, we just did that, right? 1/2, correct, class? All right, so what's the probability of A given B? Just using the Venn diagram approach. You can see it obviously just looking at the numbers there, right? What is it gonna be? 1/3. The probability of AB, I put that right there, which is gonna be 1/6 over the probability of B, or 1/2, right? And that is going to be 1/3. With me? Now, you don't have to use a Venn diagram. It's a fairly easy problem. You can reason through that, right? If you say that B occurred, well, if B occurs, and take a look at that, this right there are only 3 numbers, right?
Mm-hmm.
And with this one, there's going to be 4, 5, so it's going to be 4 there, and it will be 1/3. If you can actually do this ratio-wise, just get rid of the S, and then get the domain down to like B and A, and you can see it if you just carve out that other number. Can you follow me what I'm saying here? Do you all see it over here? I want to make sure everybody has no questions about this. It should be obvious. Now we can extend this, and we don't have to have A and B. We can have A, B, C, D, and so forth, right? I'm going to take a logical extension in a second, but I want to make sure you see this part fairly well. I'll give you problems with this too. I've got a lot of little different notes. Oh yeah, by the same token, if I gave you the probability of A occurring given B has occurred, and the probability of B, you could figure this probability out. Y'all follow me? You can do it, you can invert the procedures. Or what do they call that? Inverse engineer. You can figure out from this equation, if you have any two, you can find a third variable, or the third unknown. Okay, now, with that in mind, I'm gonna cover switches in a second, but I want to do one other problem besides the real simple ones. And I'm looking at the Venn diagrams, like, I think you can all see it. See, they're going to take this and they're going to make it more and more complicated. Here you got 4 possible things. Can you all see these 4 circles? And there's only one area of overlap. And they're going to ask all sorts of questions. Well, what's the probability of A occurring given B has occurred but C hasn't occurred? And it's basically looking at the areas and finding out really a ratio of areas. Given one thing, like I had B there occurred, what's the probability of that smaller slice inside B occurring, the overlap to A? If there was a C, go to the next thing on. If there was something like C here, if you can follow me, now that area that I'm trying to show you there is the probability of A intersect B intersect C. This would be the probability of A intersect B, and then it would be C bar. I didn't cover that yet, but I'm going to make it clear right now. If this is the set of all possible values, and this would be A, everything outside of A with inside the set is called A bar. You've probably seen some kind of notation like that before. I don't know where you saw it, but I'm assuming you have. It just means everything but A inside the set. So when we take a look at this, and it's not a very neat drawing here, but you can see this is the area of A intersect C intersect B, right there. This would be the area of A intersect B and intersect C bar. Can you all follow me on this? Right there? From that, we'll get into this, but we can easily say if AB occurred, and I'll just try to make this simple for you. Just follow me here, and I don't really want to go all the way down the path on this one, but if A and or B occurred, all right, so union AB occurred, what is the probability of C? Well, that is going to be what? All the overlapped area right there that I'm showing you were C, A, and B. I mean, basically A or B, right, occurred. That area divided by the total area that would be in A and B, but you would have to subtract off, remember before, you would subtract off this area because it's going to be counted twice. Can you all follow me in this class? Now those are the problems that take a little more thought, and I'll give these problems to you for homework and you can work them and spend some time on it. It will become obvious once you start working these, but it does take a little time to struggle through it. And when you get 4, see the number of, the more and more possible things that are overlaying, then it gets more and more irritating, the complexity, but the way you do it is the same, and I'll try to show you this later, but I want you to struggle with some of it. I've got, I want to do one example that is not by, I want to get somebody to read this. Let's see, I've done bars, there's one other symbol, this one I'm going to cover, it's not really essential, but I'll just show you this. This is mathematics, you'll see this used all the time. So, this is the set of all possible outcomes. And I'm only doing this for completeness. This should be very obvious to you. if you have something where this is C, or I'm sorry, this represents C, the big one, and then inside of here, right here, this, I'm trying to say C, everything inside this circle is B, and then this represents A. Are you with me? Well, the thing logically you see is, well, that C is greater than B, and B is greater than A in terms of probability or area. I think it's obvious the way I do it. So what they'd say is something like this. In the book, he uses the symbol members, a member of, and I'm trying to figure out where he does this. All right, what he'll say, the way it's done is would be A is a member of B is a member, those aren't C's, this is supposed to be like a horseshoe thing here, is a member of C, and I don't even like that, but what, you'll see the symbol in the book, it means member of. For instance, 1 is a member of 1, 2, 3. 1, 2, 3 is a member of 1, 2, 3, 4, 5, 6. Do you follow me? It just means it's a member of, and it's, they use this oftentimes in explanations for shorthand instead of writing out it's a member of. That's really not that important in my book, but it's done all the time. All right. One simple problem. All right. We're going to go through this one fairly quick. I'll tell you what. Can you read this? Just exercise 1-4.1. I'm going to go through it quick, but slow me down if there's anything that you're uncertain about. 1 second here. Erase. The reason I'm choosing this, I know you can get bored to tears in this class doing this basic stuff, but believe it or not, as simple as it seems, you can get confused in a hurry, sometimes with real problems. Not the die is too simple almost, but some of this stuff can get confusing. And for this problem, I don't think it's going to be that confusing. I don't recall exactly what it says, so can you tell me?
A box contains 50 diodes, of which 10 are known to be bad.
All right, we've got 50 diodes. Don't know what a diode is. And 10 are bad. Go ahead. That means 40 are good. Okay, good.
A diode is selected at random. What is the probability that is bad?
Okay, here's my Venn for this one, S. All right, so I'm going to show you, here's the bad. Here's the 10, and I'll just use B. Matter of fact, let me have just B be associated with that. So the symbol for this is B. Everything else is B naught, so B naught would be equal to A. Follow me? I'm just trying to make this as simple as possible. Now, there's going to be a logical question that everybody sees coming. What is the probability of selecting one of these diodes and being bad or good, depending on the way it's phrased? What is he asking?
If the first diode drawn from the box was good, what is the probability that the second diode drawn will be good?
All right, first, what is the probability that the first diode is good? What is the probability? First, it is good, or the probability it is good?
That it was good?
All right, first, what's the probability it's good?
4/5.
It's 4/5, isn't it? Just do the math. I mean, can you all see this? I'm getting bored. 4/5, right? All right, now, if it is good, he says that if it is good, Now, what does the remaining leave us?
with 30.
If it is good, we still have 10 bad. So now, as far as our bad goes, we still have 10. But as far as our good goes, now we have 39. Do you agree? This is a logical progression. And I'm not doing this with a Venn on this one necessarily, though we could easily do this. Go ahead.
Was the probability that second diagram will be good?
Okay. Anybody? How many see it? I'm not going to call on you. All right, what do we do here? Here's our space now, right? We had to remove that diode. This is a permutation. This is as we're moving down the probability chain, you say, as the event is occurring, we get further online. We have to take a look at our event space and what's remaining. Now our set's changed, right? The set really has 49 possible values. And if we want the probability of a good one or bad?
A good.
Well, what's the probability of a good one being drawn from this?
39 out of 49.
39 over 49. Is that one of the answers? He has the answers. All right, so that would be the first answer. Does that make sense? What's the next part?
If two diodes are drawn from the box, was the probability that they are both good?
And now what he didn't say, if it's drawn and replaced. This is the problem I didn't cover yet. So there are types of events where you can draw something, then replace it. There are types of events where you draw and do not replace. Do y'all follow me on this? He doesn't specify, which is troubling. So I'm going to say it's not replaced, and I hope I'm right. So he wants the probability. Hold on now. Let me erase this. Okay, probability that you draw one and it's good, right?
You draw two, was the probability that they're both good?
Okay, simultaneously. Okay, so I think I can do this with a Venn. Well, if you take a look at this, the probability of drawing two out of there and both are good is what they're asking for. So if you look at this, here's the good ones, and the probability of drawing them, the problem is, I wish you'd say, and draw and don't replace. I guess if you're drawing simultaneously. So it's really the probability of drawing two of those, so probability of drawing one. So that's going to be, we I'd have to do that with a Venn. That's going to be 4/5 plus. This is the probability of drawing one diode. We're going to take two, but I'm trying to do this sequentially. The probability of drawing one good diode would be 4/5. Do you follow me? Now, the remaining is going to be that 39 over 49 there. Do you all follow me? So the probability of drawing the second one probability of drawing one, two, oh, actually, I'm doing this wrong. If I look at that, too good out of 50. Is really the probability of drawing no bad ones. So it's going to be probability of drawing a bad one is 1/5. So it's going to be 1 minus, I'll explain this in a second. If squared, let's see. See, the probability of not drawing a bad one is 1/5, right? 1 minus 1/5 is the probability of drawing a good one. Do you all follow me? If you do that for 2, it would be 1 minus 1/5 squared, and this would be 4/5 squared, and what is that, 16/25. Is that an answer? He breaks, yeah, he did it exact then. So what he did is 4/5 here. I'm gonna need this number. That's the probability of drawing one good one. The next probability of drawing, if you drew that one, is going to be 39/49, right? 49. Is this, he probably multiplies it out, doesn't he? Does he have a number, a large number?
It's like 156 over 200.
Yeah, can somebody just do this for me real quick and I'm gonna move on. 156, did he say?
156 over 245.
Yeah.
That's it.
That's it.
All right, that's it, but I was trying to do it a different way. I'll explain that in a second, and the reason is because it takes me to my next point. I know I only got about 8 minutes, but you all follow me on this one here? And really is, the fact is, I didn't cover this well. Obviously, for the first time, you got that, right? Now, that's the probability of the first event happening. The second event, right, is not mutually independent. In other words, the event space has to be, or the set has to be changed because we removed one. But then the probability of the next event happening is this, and I didn't get to this, but the probability of A occurring and the probability of B occurring we're going to multiply these probabilities, and I don't have time to get all into it, but I'm going to show you something that will make it a lot more sensical. And this has to do with switches. You all know switches, binary switches, on or off. We're going to talk about switches. We're going to do it real simple. And this is going to be switches, but it's going to be with a probabilistic thing. If we have a switch and the probability that it works or it's on, I'm just going to call it as P. So the probability it works is on, right? So the probability of a connection working from here to here would just be P. I'm making it as obvious as I can. The probability of it not working, or the probability, and I'll just say of off, and really not working, is going to be 1 minus P. I was trying to go there with that one, but I can't because I got to alter the second one. All right? That's just one switch. If I take another switch and put it in series, and I'll say this is P1 here, probability of this one working is P1. So probability of not working is 1 minus P1. For this one, I'll call probability of working P2, probability of it not working 1 minus P2. Can you all follow me? Now the probability that this circuit would work from here to here the probability that the circuit would work would be equal to P1 times P2. They're in sequence, in series. If this had a 10% chance of working, or 0.1, and this had 10%, it would be 0.1 squared that the circuit works. Do y'all follow me? These are series connections. If I added another connection here, and this would be P3, then the only thing you're going to do for this circuit is the logical extension is multiplied by P3. Are you with me? Now that's the probability of the entire circuit working. What's the probability of it not working? Can you all see it?
1 minus.
Exactly. We know it's going to be 100% that that it either works or it doesn't work. There's no other outcome that's possible. Now the next part is real important. You pay attention. This is my last point. I got about 3 minutes to make it. And then we're going to do a problem. You're going to see that this can get. You'll see how this can get a little. The word would be obscure or confusing. All right, now I'm going to do this. I'm going to say I have something in parallel. I don't know if you've seen this before, but this is interesting. And the probability of this one working, P1, and the probability of this one working, P2. You with me? Now, if that's the probability it's working, the probability of not working one minus P1, and same for this one, 1 minus P2. Everybody with me? Now for this one, the way you figure out what is the probability of this circuit working from here to here, or having a zero impedance path, not an open circuit, but a closed circuit. The probability of it working, you don't go at the same way. What you have to do is take a look at the probability. What we're going to say is, well, the probability of it working is 1 minus the probability it's not working. Whenever they're in parallel, you go for the not working. You all hear me on this. This is real important. This is the problem. This concept fouls people up, I promise you, in big ways. So if you take a look at this, I'm going to say the probability the circuit works, the probability of, I'll just call it circuit, works, is going to be, well, it would be 1 minus, and then it would be the probability of this not working and this not working. Do you all follow me? Both of them can't work. If this one works, it doesn't matter if this one isn't working, and vice versa. So it's going to be 1 minus, and then you have to take the probability that this is not working, which is 1 minus P1, times the probability this one isn't working, 1 minus P2. You all follow me on that? How many see that? Now, what you can do then with this is build logically. If I have this right here, you know that's the probability of it working, right? You can replace all this crap by just one switch with probability of working P1, P2, P3. You follow me? Then, if you had this in series with this, you would just replace it by this value, probability of that working, and multiply this times that. You all follow me? Now, the one last thing I have to say before I'm done is you can extend this. You saw how I extended that to 3 layers, right? Or 3 values in series. I can extend this and add another one. Here, I'm going to ask anybody how you think you would go about that. Here's P2 here of it working, here's P3 of that one working. Now what would I do to augment that? Well, the probability of this not working is still that. This is 1 minus P2, this is 1 minus P3, but now all 3 of these can't work. Do you all follow me? And have you noticed as more and more are added, the probability of it working goes up and up and up, because each one of these things is less than 1. Do you all follow me? So if you've got the third one, it's 1 minus P3, and you can extend this indefinitely. Now I'm going to show you some other things that get complex, because you remember, did you all have power yet? Or you had circuits, right? Remember delta Y conversions? All right, now when you get delta Y networks, it gets a little hairy. I have to show you that one another day. I'm going to give you some problems. I'm going to take them out of this book I've got that you've got right there. And did you have any questions before? You can go now. It's class is technically over, but if you have any questions for me, and thank you again for doing this. Any questions at all? I don't know your names yet.
If you do the circuit not working, do you treat it like you do this series whenever power's on for the firewall circuit.
Well, what I'm trying to do is find out the probability of it working, right?
But if you're trying to find the probability of it not working, you just
I just get rid of the one.
Oh, okay.
That's it, probability of it not working.
Okay.
And it gets lower and lower and lower the more parallel layers, and it gets higher and higher and higher of it not working the more series layers. Because if any one goes bad, it doesn't work. By the way, this stuff, this is sort of the beginnings of looking at a lot of this large-scale testing theory. You know, they have built-in self-tests to VLSI chips now. The reason is the complexity in these, you know what VLSI is, very large-scale integrated circuits. Well, they're logic gates, but now you have to take a look at the probability of whatever it is functioning if one fails. And believe it or not, it's, even though it's much more complex than what I'm showing, it's built on these principles. Because if you have anything where there's redundancy, and they built this in, then you have a huge cushion for making mistakes if you have a failure, because there's always going to be problems with lithography. You can never make a structure that has no defects or no problems, and you'll find that out later. All right, thank you. Sorry I wrapped it up a little fast.